So lastly, I'd like to figure out what we can about theta halves, whether that is what sine of theta halves is or cosine of theta halves is. And before I get started, let's look at those formulas. Notice most of these formulas have plus or minus values in them. Again, these formulas do not determine whether your answer is positive or negative, and so here we have to be picky about where is theta halves and what quadrant is theta halves, and thinking about, all right, if it's in that quadrant, does that mean signs are positive or negative? So before I actually calculate any numbers, let's look at where theta halves ends up by taking this inequality and cutting everything in half. So cutting everything in half reveals that theta halves is an angle somewhere between 90 and 135 degrees. And so if I look at that picture, here's 135 degrees. Theta halves is an angle somewhere in here. And I can now decide that sines in this quadrant, in quadrant 2, above the y-axis, sines are definitely positive. Cosines are the widths. That's to the left of the y-axis, and so this is definitely a negative cosine value. And as soon as you know those, you can reciprocate them and divide them and figure out what tangents and cosecants and all that sort of stuff are. So let's fill out just the positive and negative aspect of this chart a second. This is definitely a quadrant 2 angle, and in quadrant 2, sines are positive, and their reciprocals, cosecants, must be positive as well. Cosines have to be negative, and their reciprocals, secants, will have to be negative. And cotangents and tangents are both going to be positive divided by negatives, and so those would be negative values as well. So now I can use the formulas to get the numbers involved, and I don't have to worry about whether those are positive or negative because I've already made that decision. So perhaps let's find the sine value a second. Sine of x halves uses this formula, square root of 1 minus cosine over 2. So if we write that in, and we'll need to use those numbers. So sine of theta halves is equal to the square root of 1 minus cosine of theta all over 2. I'm going to check and make sure I've got plus minus right. Yep, sine is minus. The cosine value is the same work but with a plus sign instead. So, and if we fill in our numbers now, cosine of theta was the given, and so we can write in 1 minus negative 3/5. Ooh, subtracting a negative. All right, all over 2. On top, subtracting a negative is the same thing as adding a positive, and so that reveals 8/5 on top of 2. So 8/5 cut in half is 4/5, and that's all under the square root. And maybe now I'll take a second and take the square root of the top and the bottom. Square root of 4 on top of the square root of 5, and that's 2 on top of the square root of 5. And if it were up to me, I would just be done, but the rules for simplest radical form require a square root of 5, or no square roots in the denominator, and so the way to get rid of them would be to multiply top and bottom by square roots of 5, and that gives me 5 on the bottom and 2 square roots of 5 on top. And so final answer for sine of theta halves is that it's either a positive or a negative 2 square roots of 5 over 5. And we decided earlier, because of where theta halves is, that this has to be a positive value. And so I can fill that in my chart now. A positive 2 square roots of 5 over 5. To find the cosine value, we can do very similar work, but instead of subtracting cosine of theta, we would add cosine of theta, and you can work through that and eventually get a square root of 5 over 5. Another thing that you could do is realize that this, as soon as you know sine, you can use the Pythagorean theorem to figure out what cosine is. Had this turned out to be nice integer values instead of radicals and square roots of 5, you may recognize a Pythagorean triple, which might be a shortcut. So there's lots of different ways we could figure out cosine of theta halves. I want to do one more time the right triangle idea. So if I go back to this value, sine of theta halves was 2 square roots of 5, 2 over square roots of 5, excuse me, and sine is opposite over hypotenuse. So let me draw in a triangle. Second, here's theta, and opposite would be 2, and the hypotenuse would be the square root of 5. And if I use the Pythagorean theorem a second, I could figure out what this side is. X squared plus 2 squared equals the square root of 5 squared. So that's x squared plus 4 equals 5. So x squared equals 1. So the square root of that is 1. And knowing that that's 1 now allows me to find the sine, cosine, tangent, any of those different values using the SOHCAHTOA acronym. And so the cosine value is cosine of theta would be, excuse me, that's not theta, that's theta halves. Whew, all right. Cosine of theta halves would be 1/2. I'm sorry, that's where am I? Cosine is adjacent over hypotenuse, and so the cosine of theta halves would be 1 over the square root of 5, and you can't leave it that way, so you'd have to multiply again, top and bottom, by square root of 5. That gives us a cosine value ultimately of the square root of 5 fifths, and square root of 5 fifths is negative because we decided that earlier. Quadrant 2 angles have to have negative cosines. So, and we can find the tangent by either referring to our triangle over here and looking at opposite over adjacent, which would be 2 over 1, or by dividing the two ugly fractions over here. Sine divided by cosine would be a tangent. This cleans up a lot because the square roots of 5 cancel and the fifths cancel, and so I've got a 2 on top of a 1, a negative 1. And so when you divide those out, you get a negative 2 for tangent. And then you can reciprocate each of these to get the cosecant, secant, and cotangent. So tangent's value reciprocated is 1/2. The cosecant's value, that's sine's reciprocated. Here it's helpful to remember that sine was also 2 square roots of 5, and so when you reciprocate that, square root of 5 over 2 is the cosecant value. And the secant value is the reciprocal of cosine, which is same thing as the square root of 5 over 1. And so square root of 5 over 1 is just square root of 5. That one cleans up pretty nicely. So anyway, there's all the different trig values for theta halves. And again, you can find all sorts of information if you're just given one piece. In fact, we could figure out what theta fourths are, theta eighths eventually. We could figure out what 4 theta